Welcome back. In this video, I wanted to discuss a few ways to tune the main device parameters, namely VT. Okay. How do we design a mouse device, right? So that it has a certain VT, and what are the various parameters that impact VT, and how does the CV look like when you change, let's say, doping, and when you change oxide thickness, what happens to the CV? Okay. So that will help us understand how the device works, right? So let's go back to the basic structure. We were talking about basic assembly. So I'll just make it like this. And then there is a oxide on top. This is my, okay. And there's a metal on top of this. This is my basic MOS structure, right? So this is, let's say, some substrate. Let's say we have Na. This is my TOX. So if you calculate this, if you measure the CV of such a device, you apply for, we discuss the circuit, how to do this. If you do that, what you end up getting is, let's say, a CV which looks like this. Okay. So you have this COX and this is Cmin, right? And of course, what happens when this is your VT. These are the three main parameters in the CV, right? So how do these things behave? Okay. First thing we'll ask is, what happens when you have when you increase the substrate doping? When you increase substrate doping, will the accumulation capacitance or COX change? Well, no, right? Because COX we saw was purely geometric, right? This epsilon ox divided by TOX, purely geometric. Okay, so this does not change with any. It does not change with any. Okay. That's good news, part of it. Okay. So what happens to Cmin? Will Cmin change with any? Right. To understand that, what happens when you increase Na, the substrate doping increases, then the depletion width is going to reduce, right? You don't need to uncover as much charge, as much deeper into the semiconductor, right? So depletion, W depletion reduces. That implies that your C depletion is going to increase. Therefore, your Cmin, which is going to be COX, C depletion divided by COX plus C depletion, this is going to increase. Because you see, when you have sort of a sum, right, it will be close to the smallest number, okay, always. Okay, if the ratio is large, then it will be almost equal to the lowest number. Okay? So, what happens when Na increases? Well, it turns out that it increases in this fashion. Cmin increases. Okay, this is one thing that we will expect as Na increases. Let's say what happens if your oxide thickness increases. Okay. If your oxide thickness increases, let me put it in the, okay. So, TOX increases, what should happen? Well, one of the consequences, straightforward consequences, COX will reduce. Capacitance of the oxide will reduce. So this implies gate has weaker control, right? You don't really have a sufficient ability to deplete or invert. You need to, so you'll be much weaker control. Essentially, that's what it is, right? So how does the gate voltage fall across the oxide in semiconductor? So VG we have seen is basically minus QD by COX plus surface potential, right? And this is essentially going to be V oxide. So this increases because, COX decreases, yeah. COX decreases, so V oxide increases. So if you have the same voltage, okay, then your phi s has to be smaller, right? If you, for a particular voltage VG, right, for a particular VG, TOX increases implies phi s has to reduce because oxide is going to take a much larger fraction of the voltage. Okay. So if phi s decreases, what happens to the W depletion? The width of the depletion region is simply square root of 2 epsilon silicon Na divided by divided by Q Na times phi s. So W depletion reduces, That implies C depletion increases. Okay. So basically, again, if you have even a same oxide thickness reducing, TOX increase, right? TOX increases, Na increases. Both cases, Cmin will increase. Okay. So this is what we would expect from a Cmin increases as TOX increases. Well, this is what we'd expect. So what I did was I went to NanoHub and then I grabbed a few CVs. I downloaded them and then I plotted them, cleaned up a little bit. So this is what you get. So I use 3 different doping concentrations. So 10 power 14, 15, 16, and then you run a same CV. Okay. So in this case, what I did was I took a substrate thickness of oxide is 0.1 micron and P plus polysilicon. So you yourself can actually verify this for yourself. Okay. So if you take 10 power, let's say 10 power 15 concentration, your VT was somewhere around 1.5 volt or something. Okay. So what you notice is clearly the Cmin is increasing, right? This is what we were talking about in the last class, the last slide, right? So Cmin increases, and in a way that is sensible, because what does increasing the doping of the semiconductor mean, right? So what you have is a metal oxide and a semiconductor, right? Semiconductor. Now, if Na increases, semiconductor behaves more like a metal, isn't it? So effectively, you're kind of approaching the parallel plate capacitor sort of a structure. How does the CV of a parallel plate capacitor look like? Well, it will be flat, constant, right? It doesn't change. It's fixed number. So as you increase the doping concentration, you are approaching the parallel plate capacitor. Okay, that is one aspect. The other aspect, if you notice, this point where the HF, this LFC starts going up, right? This is basically threshold, right? So VT is increasing as Na is increasing. Why does that happen? Right? So, well, remember what is VT? VT is minus QD by Cox plus phi s, right? Or 2 phi f, right? VT is 2 phi f. So QD is basically proportional. This guy is proportional to Na. As you increase the doping concentration, VT is going to increase. If you don't want a very high doping concentration, you have to use a low Na. Sorry, if you don't want a high VT, you need to use a low Na. But then if you have low Na, there will be some other side effects. Okay, we will. I mean, if you're actually doing the device design, you have to take care of all these things. Okay, then what happens to the oxide thickness dependence? We are again seeing the same trend. So basically, Cmin increases as Tox increases, right? So this was done with a slightly different. I deliberately chose now. Oh well, I wrote Na here, but that is incorrect. This should be Nd, right? This is a PMOS device, so it has to be N-type substrate. Okay? So Nd, that is 10 power 15, and N plus poly. Okay, yeah, N plus poly over NMOS, N-type semiconductor. Okay, so you see that Vt is typically in the range of 1 volt. I'm deliberately mentioning this so that I'll compare it. I'll ask you also to compare. In the last video, we mentioned that if you have an N-type substrate, use a P plus, and if you have a P-type substrate, use an N plus. Okay, that has advantages. It will lower the VT, I said, right? So you can verify that yourself. Okay. So anyway, as the thickness of oxide is increasing, we explained this trend already, and there is a small dependence on VT again here, right? VT in magnitude is increasing. Why is that happening? Well, if your thickness Tox is increasing, Cox is reducing, so your QD by Cox is going to increase. So VT is going to increase. But you see, it's not that much of an effect, okay, as compared to Na. It's a much weaker effect. It seems to be that, right? Okay. All right. So one of the Okay, yeah, I'll mention that again. Okay. So now let's move on to the next thing, that is basically temperature dependence. This is again another thing that you can simulate on nanohub and check. Okay. So in this case, deliberately, I chose a p-type substrate and an n plus poly. If I do that, you'll notice that the VT is close to zero. I mean, it will be 0.1, 0.2, something like that, right? So see the distinction when I use a p-type and p plus poly. It was 1, 1.2, something like that, right? 1.5. But now if I use a n plus poly, I'm actually reducing the absolute magnitude of my VT. Okay. And as temperature increases, as T increases, you have more EHP pairs, right? Generated, right? pH generated in depletion. Okay. So if you have more EHP pairs, essentially this behaves more like a standard capacitor, right? So it tends to go up. Okay. So, and also one important thing to notice here, right? Accumulation and depletion not uh, significantly affected. Inversion is where you have the problem, because inversion is the minority carrier response. And if it is not fast enough, we know how it behaves, right? So inversion is something that you have to always pay attention to. Okay. Yeah, because we also said this is because of it's dominated by majority carriers, right? Majority carrier response, and they are quite fast in responding. And okay, this is how the temperature changes. So you see that as you go to higher and higher temperatures, there is a very significant increase in the minority carriers. So that tends to screw up your devices. Okay. So that's why electronic devices, whenever they get heated, it's not good for their lifetime. They spoil and they get spoiled much faster. So whenever your laptop or computer is getting heated up aggressively, then you have to really think about what's happening, and it might actually be approaching the end of its life. Okay. All right. So this was the parameter dependence that I wanted to talk about. One last thing I wanted to just come back to before I stop the discussion of mass capacitors is gate oxide scaling. Okay. So we saw that basically this slide, I think the first video on mass capacitor I showed you this, and I mentioned that over the time the thickness of the gate oxide kept on reducing. The reason it was reducing is if your P oxide reduces, C oxide increases. Okay. This implies that you have greater capacitive control on carriers. Okay. So essentially, we are eventually, from next lecture we are talking next week we are going to talk about MOSFETs. Okay, MOSFETs are essentially devices where you switch off current and switch on current. You want to have a very strong control on that. You don't want to have a weak control. So one of the requirements was always to use COX. Okay, and we will see very soon in the next couple of next week lectures that ID, the drain current, which is one of the important parameters in a MOSFET, that is going to be proportional to COX. So if your COX is large, your ID is going to be large. If ID is large, then the transistor works faster. I mean, it essentially charge and discharge faster. Okay, so this is one of the main effects. Okay, so because of this, over the last 40, 45 years, scientists, technologists have been scaling down the oxide thickness. Okay, so now what happened was, as you do this, by the year 2007, okay, by I would say even 2005, excuse me, SiO2 thickness was 1.2 nanometers. This implies that it's essentially 4 to 5 monolayers, 4 to 5 atomic layers thick. I mentioned this fact already. So if you have very thin SiO2 as shown in the picture as well here, right? So this is a very thin thickness of SiO2, and because of that, you can have strong leakage. So we showed the band diagram of a MOSFET before. So essentially, you can have electrons which are tunneling from the metal into the semiconductor, because this thickness is now 1 to 2 nanometers, right? 1.2 nanometers, whatever. So you can have a strong leakage. Okay, electrons tunnel, uh, giving rise to leakage current. Okay. What happens when the oxide leaks? Capacitor action is lost. Okay. Capacitor action is lost. So as we were talking, so when there is tunneling of electrons into the oxide, through the oxide, there is leakage current, and leakage current is going to spoil the capacitive action. Okay. So how do we, get around that? Well, we are having two opposite requirements. If you want to reduce tunneling, you need to have a thicker oxide. But if you want to have a strong gate, capacitive action, right? You have to have a strong COX. That means COX has to be large. That implies TOX has to be small. So there are these two counterproductive things, and there is nothing much that could be done till 2007. Okay. So in 2007, Intel came up with this. I mean, the idea was there for a long time, but practically Intel introduced the technology in 2007. What they did was, remember what is COX? COX is epsilon oxide by thickness of oxide. So all the time we have been reducing this. Reduce TOX, right? Till 2007, I would say. But then there's another lever that we have, which is increase epsilon oxide. That also has a similar effect, right? So what does increase epsilon oxide mean? Well, oxide cannot be, oxide's material parameters are fixed. We can't do much about it. But it turns out that we can replace, the idea is replace silicon dioxide with a high K dielectric. Okay. What do we mean by high K dielectric? Well, it is something, high dielectric constant essentially. So this epsilon relative of, let's say this is an example will be hafnium dioxide, is one of the high K dielectrics, is about 25. So essentially silicon dioxide epsilon relative of SiO2, which we have been using so far, is 3.9. So instead of using 3.9, use hafnium dioxide instead of silicon dioxide. Okay, that was the approach that was finally demonstrated. It's been known since I think 90s, early 90s. But finally, Intel managed to demonstrate it in 2007. Okay, the Intel Pendrain processors, right, 45 nanometer technology was actually based on this. Okay, so we replace this by high K dielectric. So what? Well, what it effectively lets you do is, like, let's imagine, for same capacitive control, okay, capacitive control, right? Essentially, I should have the oxide capacitance, or gate capacitance should be same, right? So what I'll do is epsilon oxide divided by T oxide should be equal to epsilon high K divided by thickness of high K. Okay, so what this implies is I can quickly write thickness of high K, right? T high K should be equal to epsilon of high K divided by epsilon of oxide into thickness of oxide. Okay, so this is 25 divided by 3.9 into TOX. So in 2007 it was 1.2 nanometers. 2005 it was 1.5 nanometer, 1.2 nanometers. So immediately, if you just replace silicon dioxide with hafnium dioxide, you could have thickness of high K to be about 6 nanometers. So you're able to get a physically thick gate oxide and still have the same capacitive control, or same current, because COX is still the same. Okay, so this was it was a simple idea, but once you increase the thickness, this tunneling, quantum tunneling is avoided. Quantum tunneling is reduced. just by using different material. But well, it's not that simple because in the beginning of MOS devices itself, I mentioned that one of the great features of silicon dioxide system was that the quality of the interface was very large, very good, right? So there are very, very few defects. But the moment you use hafnium dioxide, or there are a few other class of dielectrics, all these high K dielectrics. So if you use them, the interface quality turns out to be not so good. So it required a lot of technological achievements to make sure that it works in real life. Okay, so it is not a simple problem. I'm sure quite a few $1 billion were spent on this to actually make this process work. But once it was achieved, the processors were able to go faster. The scaling continued, and we will talk more about it. This is what we would call as scaling. So I'll give you a small problem in the assignment based on the high K dielectrics. Just compute some numbers, okay? Or maybe one of these problems I'll do it for high K so that you get an exposure of what it is, okay? And then we will understand. This is just one aspect of scaling. The thickness of the oxide is reducing. We will talk about other aspects once we discuss the basic MOSFET, okay? So now the plan is that in the next, I'll record one more short video using, showing you some CV examples from NanoHub. By now you should be comfortable, but anyway, I'll just go ahead and show you a few things which I think are important. You can either follow along on your own, or you can try to explore and see what it is. That will help you, refresh the things that we are learning here. So that's an interactive learning tool, and I'm fond of it, and I think it will be very useful. So I'll record that short video, 10-15 minutes or so, and then I'll stop. So that will be the end of the MOS capacitor discussion. And in the next week, we will start off with MOSFETs. Okay. So, all right. Thank you so much for your attention, and I hope you're having a great time learning this. I'll see you next week. Bye.